video, what I'm going to do is I'm going to prepare you for quiz 8. So what we're going to do is we're going to go over the advanced rules of formal logic. That's everything from biconditional ponens to dispersion. These are things that are going to make your proofs more efficient. You're going to be able to skip out of a lot of steps. And so I'm going to go through each rule here and show how to do them. And then in the next video, I'm going to show you how to apply them in particular proofs. Let's do it. For this quiz 8 prep, let's take a look first of all at where to go. So if you go to here in Blackboard, you go to course content, and you go to rule guides. There's two things here that have been here all semester long that have been updated since the beginning of the semester to reflect just a few tweaks here and there. But first of all, there's this formal logic basic rules. But I say basic because these are all the rules up to this point. Okay, basically for the first wave plus, we'll say for the first wave, all the rules here plus the stuff on disjunctions. It's really up to and including quiz 6, 7. So everything up to this point is here. And it also, this follows the order in which you should do things. Look, it starts out with arrow out, modus tollens, double arrow out, double arrow in, and out and in, double negation, wedge in, wedge out, De Morgan's law, material implication, conjunctive conditionality, conditional proof, and indirect proof. Okay, so those are the 14 main moves. Okay, every single problem, every single logic problem in this class can be solved with simply these 14 moves. Okay, some will take longer than others. Okay, again, there's stuff in predicate logic and modal logic. That's stuff with the backwards E's, the upside down A's, the squares and diamonds. That would need some more rules to solve those kind of things. But all the problems you're going to have in this class are solvable. The proofs are solvable with these 14 moves. In spite of that, however, if I go back up here to the rule guides, there's this other one here that says advanced rules of formal logic. Quiz 8 is going to be about the implementation of these. And so what I'm going to do for the next major chunk of this video is I'm basically going to go down the list of these moves and how to use them. And here, these are kind of in a random order because there's no real right order at this point with these being included. So if I go down the list, you'll notice we had our 14. These are 20 additional moves, making your move set up to a full 34. 34 different moves you can use. Now, when we get to quiz 8, again, every problem can be solved with the basic set of 14. However, some of those problems are going to take you a long time if you go about it that way. So really, quiz 8 is about looking, where can I use these advanced rules? And I know it says advanced, and that makes it sound like it's more sophisticated. Honestly, the advanced rules are shortcuts. As I go through the majority of these, I'll give a rough estimate. I'll say probably 80 to 85% of these are actually moves that allow us to do things that we've already done this semester just much more quickly. And I've previewed some of them. I've said, oh, later in the semester, we'll do something that will allow us to do this proof that took a long time in one step. Most of these moves are going to be just that. Some of them are going to be that, but they're going to be a little bit more complicated to spot. So that's what makes some of them a bit more challenging. And then what I'm going to do is after I go through this list, I'm going to give you a new recommended order for how to approach problems on quiz 8, and then we're going to go into some on quiz 8. So let's start going down the list here. All right, first rule I want to take a look at. This one's very straightforward and saves us a few steps. Biconditional ponens. So it's kind of exactly what it sounds like. So if we were given this scenario, so way back on, say, quiz 4, let's say I had this. Okay, we got A, double arrow B. We've got A, and I said, hey, solve for B. Well, what we would have had to do back then, based on the rules that we had, so if we go just off the basic 14, oh, we've got a double arrow. What we can do is we can break it apart. We get A, double arrow B. We get B, double arrow A. That would be double arrow out on line 1 for both. And what we can do now is, oh, do we have an arrow? Can we do we have any left side matches? Yeah, now we do. So we can say, hey, line 5 here, A, arrow out 3 and 2. Okay. So this is based on the basic rules. This is what we would have done. But let's see how biconditional ponens actually helps us here. So let me revert back to just having the first two lines. So the rule for biconditional ponens allows us to do exactly this. It's basically, instead of, it's I don't want to say, it's not arrow out and it's not double arrow out, but it's basically an arrow out for double arrows, which is to say this. If you have a double arrow and you have a match of, really because it's a double arrow, the left side or the right side. If you have a left side match or a right side match, you can then say, oh, I've got the other one. Okay, so we can just say here, B. Okay, and what is it? Biconditional ponens, 1 and 2. Now again, remember, it doesn't have to be, if it's double arrows, it doesn't have to be a left side match, it could be a right side match. So I could have this, if I said a double arrow B, and I said, oh, you've got B. Well, then I can say, hey, you can just get A. Biconditional ponens, 1 and 2 still. Okay, that does not work with arrows that way. So this is a special thing with double arrows that you can see just shaves off 2 steps. So like I said, that's what a lot of these rules do, is they just shave off a couple of steps. And some of them shave off more steps than others. Okay, so let's take a look now at one. If this one is sort of a arrow out for double arrows, the next one is basically a modus tollens for double arrows. But now with biconditional tollens in play, and let's just say I had this. Let's say, and this is going off exactly the example in the advanced rules document. Let's say A stands for two-dimensional shape is a triangle, and B stands for the shape has 3 sides. So it's a triangle if and only if it has 3 sides. Okay, well, it's not a triangle. Then what do we know? It doesn't have 3 sides. Biconditional tollens. Okay? But again, the way this one works, it's not an arrow. So we remember in modus tollens we need to have a contrary of the right side. But since it's a double arrow, both sides are the left side and the right side. Okay? And we can see that if we do a double arrow out, but this is trying to avoid doing that extra step. But what that also means is we could have something like this. Okay, same one, and I could have the negation of the other side, squiggle B. Okay, and again, same values. Okay, it's a triangle if and only if it has 3 sides. Well, it doesn't have 3 sides. Well, then it's not a triangle. Okay, biconditional tollens. Oh, and these are 1 and 2 for both. Okay, just again, all this does here is it shaves off a couple of extra steps. Let's take a look at the next one, which is a bit more complicated because of its rarity to figure out when to use it. But when you can find out that you can use it, it actually saves you considerable time. Let's take a look. All right, so the rule we're going to look at now is destructive dilemma, aka reversed wedge out. Okay, now let's do a quick refresher on what wedge out is. So remember there we could have one of 2 options. We could have going in X or just plain old or. And it looks like this. Okay, you got, and there's 2 versions. There's a redundant version and a distinct version, proof by cases. So here's what you got in either version. You got an or statement, and each of your disjuncts, that is your or parts, are themselves antecedents, that is, they're each also separately on the left side of some arrow. And in this case, if the resulting consequent is identical, you can just say, hey, then you get that thing. Then there's another version of this where the resulting consequents are distinct, and in that situation, you can simply say, yeah, so you get the results as an inclusive disjunction. You can never get a XOR out. Same thing here. It's reverse or out, reverse wedge out. You're never going to get an XOR out of this. Okay, but how does this work? Well, it's really this in reverse. So let me take a look at the most basic version of a destructive dilemma. Okay, so and let me say what to look for and how it's different from this. Okay, it's basically an inverted form of this. Okay, so let's take a look at this. Let's say we had squiggle C, wedge, squiggle D as an assumption. Let's also say that we had A arrow C, and let's say that we had B arrow D. Assumptions. Okay, now this kind of looks like this. In fact, it is. So think about this here, all right, what we've got. So in fact, two of these, even just in the model here, are identical to two of these. Okay, and this looks like the individuated negations of this disjunctive result here. So let's take a look at what this would say. Think about it. All right, and I'm going to put the model that I used when I was talking about disjunctions earlier too. Let's say I had something like this. All right, to illustrate what's going on here, I put a little diagram that I used earlier in the semester to explain regular wedge outs. So in this scenario, you can think of it as like these arrows as like two slides. This thing or this thing is happening. Like you can go down the red slide, you can go down the blue slide. If you go down the red slide, you're going to end up, at this sand pit at the bottom. If you go down the blue slide, you're going to end up this ball pit at the bottom. Cool. Now, then look at here what's going on here. We've actually still got the same slide things going on. Let's use the example of what I just said out loud. Okay? You take the red slide, it leads you to the sand pit. You take the blue slide, it leads you to the ball pit. Okay? Red slide to sand pit, blue slide to ball pit. Well, but then we've got this here that says, okay, you didn't end up in the sand pit or you didn't end up in the ball pit. Neither one of those results happened. So these arrows are true, but this thing didn't happen. Okay, so we put that here. This thing didn't happen. Nor this. Neither this nor that. All right, so this one didn't happen. This one didn't happen. So what do we know from that? Well, then you didn't go down either slide. So that's the result, which means that's what we get. We can say we get squiggle A, wedge, squiggle B. And that's a reverse wedge out. I'd say 1, 2, 3. So the technical way I'd say to look for when to do this is this. Do you have, and again, it's the inverted form of wedge out. But here's what you look for. Look for, do I have a wedge? Okay, great. Now look at your disjuncts. So in a wedge out, what we looked and saw, all right, we looked, do we have a disjunction? Yeah, and it could be that we could have started with an XOR. No matter what, though, you'll always get inclusive OR out. So here's what you do. Regular wedge out, you look for, do I have a disjunction? Yes. And then you look for, are each one of my disjunctions left side matches? If so, you get the right side together if they're different as a inclusive disjunction. Same thing in reverse, right? Look and see, oh, I have a either kind of disjunction. Look at my disjuncts. Are they the contraries of the right sides of arrows? So you want to look for your or parts here. Is each one of them's contrary on the right side of an arrow? So look, I've got squiggle C. What's the contrary of squiggle C? Just plain old C. There it is. Yep, it's on the right side of an arrow. What's the contrary of squiggle D? Well, that would be just D. It's on the right side of an arrow. And what that means is if you got that, then you can put the left sides of those arrows together as a contrary. And I think this diagram is the most helpful way to look at it. Now, the one thing that I want to stress here is that this problem is solvable without doing the reverse OR out. But notice, look, we only had to do one thing. Given these three assumptions, we only had to do one move and we were done. If you didn't have that in play, let me try and do this one as simply as possible without doing a reverse OR out and see what we get. Let's just see. All right, so let's try this without using the reverse wedge out just to see how it goes. So I'm going to try and consign myself to not using any of the other advanced rules, only using basic rules to see if it's doable. So first thing that I want to do is I like to avoid having, if I can make things that are arrows or dots where there's not squiggles on the outside, I'm going to do that. So this thing I'm going to go ahead and switch into an arrow, line 1. So I'm going to go ahead and say C arrow squiggle D. Not B, but D. Alright, great. That is material implication on line 1. Already there's some other moves I could do if I use some other advanced rules. Like I can do a hypothetical syllogism here if I really wanted to, but I'm going to just keep myself limited to the basic rules. So that doesn't seem to go anywhere. Let's see. This goal, what I'm going to do is I'm going to think backwards. I'm going to think back to see if I could do, let's see, what would it be if it were an arrow? It would be A, arrow, squiggle B. And so then if I did a material implication on that, that would work. So what I'm going to do is I'm going to do an arrow in of this, and if that works, then I can just transform it into this with another material implication. So let's try that. Since that's an arrow, I'm going to have to prove it this way. Line 5, stick that A in there as a provisional assumption, and I'm going to go after squiggle B. That's the mission. Okay, can I get squiggle B? Okay, with this A, can I do an arrow out now? Well, I've got 3 arrows in play. Yeah, so let's see, I get just arrow out, that gets me C, arrow out 1 and 5. And then with C, I can get squiggle D, arrow out 4 and 6. And then with squiggle D, I can't do an arrow out here, but I can do a modus tollens that gets me squiggle B, modus tollens 3 and 7. Okay, so I did it. So I'm able to say here in line 9, okay, yeah, A leads to squiggle B, arrow in, 5 through 8, and then I can convert this into my final material implication. Remember, you can just change the left side, and I saw that I could do that. I like dealing with arrows instead of ors if I can avoid it. So now I can just convert that. Remember, to turn in the move to turn an arrow into a wedge and vice versa, you only just change the left negation slot. So that's turn it back into a wedge. See? That's material implication on line 9. And so great, it's doable with only the basic rules, only the 14. But look what step am I done in? Step 10. If I had done the reverse wedge out, remember we could have had this in line 4 and just been done like immediately, just with the 3 things we were given. You can just say, oh yep, you can totally get that wedge out 1, 2, 3. So this kind of rule is a rule that really demonstrates how knowing that it's available for use can save you a bunch of time. Literally, this went from us having to do, if we use the right rule, and we could just say none of this, you can just say, oh yeah, step 4, squiggle A, wedge, squiggle B, reverse or out, 1, 2, 3, and you're done instead of doing all of this. So that saved us what? 1 move versus how many moves did we actually have to do? 1, 2, 3, 4, 5, 6, 7. Would you rather do 1 move or 7 moves? And that's really what a lot of quiz 8 is about. Being more efficient by making ourselves more familiar with these finishing blows. So I want to take a look at a couple of other reverse wedge out situations, just so you know what's going on there. But this is the basic overview so far. Okay, where reverse wedge out gets strange is that it's on the redundant version, the redundancy works in an inverted way, not a reversed way. So here's what I mean by that. Whereas the wedge out version, where you've got a redundancy, so if you had this, remember, okay, A leads to C, B leads to C. And so what that means is we've got a model that looks like this. You have 2 slides, if you will. This slide leads to here. This slide leads to here. Okay, so that's a version of wedge out. So what we have here would be squiggle B, wedge, squiggle C, A arrow B, and A arrow C. Now this does not correspond to this. This would actually be a new model. So here's what looks like what's going on in this model. We've actually got A as a singular antecedent. A can lead to B, but A can also lead to C. Okay, so this looks like what's going on here. Okay, this would be the result. So, for example, if you get on, say, I-20 in Aiken, you can take I-20 to Atlanta, or you could take I-20 to Columbia, or both. And you might be thinking, no, you have to pick a direction. Well, just because you went to Columbia today doesn't mean you can't go to Atlanta. It's a drive, but you can do that because you've made it to I-20 now, so you can use I-20 either way. Also, if you went to Columbia today, maybe you'll go there tomorrow, or at some point in the future. You've made it there, you can do it. Okay, so that means you've made it to I-20. You can go that way, or maybe both. Maybe you get on eastbound and you realize, oh, I was supposed to go in the other direction, and so you turn around. So it can be both. But so think about what's going on in this situation. What this is saying here in the line 1 is, well, you're not going eastbound on I-20, or you're not going westbound on I-20. So based on this model, what do I know? I'm not on I-20. So what's the result here? What do we get? What I just said. We know then, just plain old squiggle A. Okay, so if one of these two things, with this situation, now this is very similar to the technique that I said about reverse wedge out a moment ago. Look for, do I have an OR? Do I have a wedge? Do I have an XOR? You can have either one at the start. Okay, doesn't matter. You'll never get one out. In this case, it doesn't really matter. Okay, so look for then look at my disjuncts, my OR parts. Look for, do I have each of these do each of these have a contrary on the right side of an arrow? So look, here we've got squiggle B. Its contrary would be B. Do I have that on the right side of an arrow? Yup. So look at this one. Its contrary, it's squiggle C, so its contrary would be C. Do I have it on the right side of an arrow? Yup. Well, then what you can do is you can put the left sides of those arrows together as a disjunction with a squiggle in front of each of them. But since it's the same, there's no point in writing you're not on I-20 or you're not on I-20 or both. This is what we call a tautology in logic. Okay, something so obvious that of course it's true. So when it comes to this kind of deduction, we can just put it this way. We can just say, yep, neither one of these results happen. You say this leads to this and this leads to this. Well, then this didn't happen in the first place. That's what's going on here. Now, on that advanced rules sheet, the other two examples simply have XORs as starters instead of inclusive ORs. The actual way that reverse wedge out functions is no different. Just make sure, just like with wedge out, make sure you can put an XOR in, but you can never get an XOR as a result. All right, the next three that I want to talk about, they're abbreviated this way so that we don't mix them up. I'd like to call them different things, but I'm going to call them this in this class just to make it simple. We've got the law of distributivity, or distribution and factoring, the distributive property. But if I call it DP, that'll mix it up with dispersion. We've got the law of associativity, or association, or the associative property. And then we've got the law of commutativity, commutation, or the commutative property. And these are ones that you use these, I guarantee you, in algebra at some point. Now maybe you've forgotten that for good reasons or for bad reasons, but let's go over what they're going to be here. All right, so these are ones, I'll say association and commutation are ones that really just make things very simple. They let us do some things that end up saving a lot of time that go back to quiz 2 and quiz 3 stuff. Just saves us a few steps. Distribution, on the other hand, or the distributive property, the law of distribution, allows us to do a ton of stuff. Okay, by that I mean it saves us a huge amount of time. Okay, and I'm going to show you how. So let's take a look at the distributive property first of all, and what it tells us we can do, because we've actually seen it before. This law of distributivity, or distribution, this is probably the most valuable rule that you have because of how much work it saves you. So keep in mind, the way that this thing works, where these rules of substitution, what this symbol means here, remember this symbol by itself would mean you can get this. If you see this, this means it can go this way and it can go this way. So this is kind of like another way of saying that you could stick a double arrow between them, which is the kind of the logical version of an equal sign. It's kind of the same thing. This is really the same thing as this. It's kind of like saying, something like, 10 plus 10 is the same thing as 30 minus 10. Yeah, it looks different, but that's 20, by the way. But it looks different, but it's really different ways of saying the same thing. So for this, what you'd want to do is we'd want to see, using basic rules, just to show you how much work this saves you. using basic rules, I want to see what this problem would look like. Okay, if this were a double arrow, how would I get from this to this? Okay, how would I get from this to this, as well as from this to this? So that's a double arrow. So basically, I'd need to do two arrow ins to make this work. What would that look like using nothing but the basic rules? Well, it would look like this. So look how many steps this proof is. Okay, and all I'm doing here is I was doing that double arrow in. Look, last move, double arrow in. Okay, how many steps? 39. 39 steps. So here's one arrow in. I did it. Okay, PA the left side, got the right. In fact, this half of it corresponds to, I think, number 13 in the previous lecture and in the chapter on disjunctions. This half of it is that. But then the other half, we had to prove the arrow in the other way, so we could do the double arrow in between them. In fact, the first move has to be a provisional assumption in order to even get this thing jump started. So look at this monstrosity. 39 moves. Okay, so if you ever wanted to distribute or factor, okay, this is simply a proof saying you can go both. You can. It works both ways. It is a rule of substitution. It works. You'd have to do this every single time. So distribution is a valuable rule because it allows us to, instead of saying, well, here's all these 39 things, instead you can simply say law of distribution on line 1. So that would be my preference. And so you see there's so it was that double arrow, that rule of substitution. We can start with this and get this, or we can start with this and get this. Just like double negation is a rule of substitution. You can start with squiggle squiggle A and go to A, or you can start from A and go to squiggle squiggle A. It goes either way. De Morgan's law and conjunctive conditionality and material implication, those are all rules of substitution as well. And so I think it's intuitive looking at it, but in order to prove it without using the rule here, the law of distributivity or distribution or the distributive property, call it what you want, but this is going to be my abbreviation for it, LD. This saves you so much time. And so that's why when we get to quiz 8, this is really the first move you should see, can I do this? So all semester long, up to this point, it's been arrow out, arrow out, arrow out. Can I see if I can do an arrow out? This is now your go-to move. Can I do this one? So look for this. Okay? And so really what's going on here is technically we have two modes. We're doing it two different directions. This is really distribution. Okay, and think of what we got here. All right, think of what we got. We've got this A, and we're distributing the A amongst the B wedge C in order to get A and B, or A and C. Like, consider this example. Let's say I said, I'm going to the movies, and I'll either see the Fincher film or the Spielberg movie. Okay, that means if I distribute this, I'm going to the movies. Well, then I'm going to the movies, and I'll see the Fincher film, or I'm going to the movies, and I'll see the Spielberg film. Okay, that's distributing. All right, taking this amongst the dots and spreading it out. Okay, also here, going the other way is technically factoring, right, instead of distribution. But we're not going to have to distinguish between calling it distribution and factoring. We're just going to go the whole thing. This law, this principle of distributivity, okay, or distribution. Yeah, technically when it's this way, it's factoring. So here we can see I could say the exact same example. Okay, I'm going to the movies, and I'll see the Spielberg film, or I'm going to the movies and I'll see the Fincher film. Or I think it was the reverse. Okay, so it was actually, I'm going to the movies and I'll see the Fincher film, or I'm going to the movies and I'll see the Spielberg film. Well, that's the same thing as saying then. I can factor the I'm going to the movies out and say, okay, so I'm going to the movies and I'll see the Fincher film or the Spielberg film. That's what's going on there. So factoring is just doing the same thing in reverse. Okay, so here we're distributing, we're taking this A and spreading it out. factoring is where we say, okay, oh, there's a redundancy here. I could, suck it out and put it to the side over here. So if I read this back, this would be like saying, I'm going to the movies and I'll see the Fincher film, or I'm going to the movies and I'll see the Spielberg film. So what I can say is, okay, so you're going to the movies. That's been factored out. And you'll see the Fincher film or the Spielberg film. Okay. So again, we don't need to distinguish between distribution and factoring. Technically, when you're doing it this way, when you're taking the thing that's redundant and getting it out to make it less redundant, that's the factoring. And when you're spreading out the joy here, that's technically distribution. But we're just going to refer to the whole thing as the law of distributivity or the distributive property. Okay, again, saves you a ton of time. Now here, on this version of it, we could have, instead of these inclusive ORs, you could have XORs here too. So these could be XORs and it would still work. Okay, so this is one version of distribution. Now there's another model of distribution that I want to talk about as well. Okay, so here what's going on is we're spreading out the and. Okay, the conjunction is being what's spread out. If we got A and B wedge C, it's the same thing as saying A and B wedge A and C and vice versa. Here's another take on distribution. Let's look at another one. All right, so this is the one that we just did. All right, this kind of distribution. We can even call this conjunctive distribution. We're basically spreading out the and. Okay, spreading that out. Okay, and it could be the disjunction that we're messing with it could be inclusive or exclusive, because the thing actually being, in this case, being distributed. If we think of this as distribution, we're distributing a conjunction, and here, if we're going from this way to this way, we're factoring out a conjunct or an and piece. This similarity is being factored out when we look at it this way. Here's another kind of distribution that you could have, though, and it's this. We could have disjunctive distribution. And the way disjunctive distribution would look is this. Basically, it's going to be the exact same thing, except I'm going to switch out for inclusive ORs. So if we had this, all right, let's say we had this, what would it distribute out to? Okay, what would that get us? Well, spread out the love, you would get A wedge B and A wedge C. And then, of course, if you had this, you could factor out the disjunct here, and you would get this. Okay, so this is conjunctive distribution, and this is disjunctive distribution and factoring. So when we're going from this to this, we're distributing the disjunct here, this A, okay, from this to this. So if I said, here's the example. Henry V. Okay, this is the example. Henry V is vassal to the King of France, or he's the King of England and the Duke of Normandy. Okay, so he's vassal to the King of France, or he's the King of England and the Duke of Normandy. As it turns out, Henry V was all those things. So what that means is Henry's a vassal to the King of France, or he's the King of England, and he's a vassal to the King of France, or he's the Duke of Normandy. It's a complicated way of saying it, but think of the kings always having their titles, and sometimes their titles are in conflict with each other. So I just mentioned Henry V. You could think of a bunch of rulers throughout history. Say, I don't know, Charles V or Karl de Fumpf. All right, he's both Holy Roman Emperor and King of Spain, and sometimes those jobs come into conflict with one another. You have that with a lot of big empires like the Habsburgs and whatnot. But the thing I want to stress here is that this is disjunctive distribution. Let me come out and say it. This is not a thing. Nope, nope, nope. Can you factor out or distribute an XOR? Okay. All right, and actually the symbol for nope, you cannot do that, is that. Okay? This is saying this is not a rule of substitution. So trying to use solely an XOR here, this is what I want to stress. Okay? No. This is fine. Inclusive distribution. Now, wait a minute. You said that I could use this here. Well, look, what's being distributed here is the conjunction. And what's being factored out here is the conjunct. What's being distributed here is a disjunction, inclusive disjunction, and what's being factored out, when we think of it this way, is an inclusive disjunct. What you cannot do is this. You cannot distribute an exclusive disjunction, and you cannot factor out an exclusive disjunct. Does not work. So this, don't do it. Don't even look at it. That's a situational fallacy. So these are the versions in play. Either one of them is fine. Okay, helpful rule. Let's now take a look at another one of those laws. This was distribution. Let's take a look at the law of associativity. All right, the law of associativity, or the associative property, or just association, we're going to call it LA. This one's great because for like way back stuff on quiz 2, it's a shortcut. And so here's how associativity works. It means you can switch things around and they mean the same thing. It doesn't change. So what's associative? Okay, well, consider this way early on. Let's say I had like a quiz 2 problem. A and B and C. And I said, get A and B and C. Okay, now, of course, saying these out loud, because if it's all ands, it makes no difference. So what we had to do back then was, remember, we had to break it apart and go, okay, we got A and then B and C. And then we had to break that down, B, C. And then we had to start building it together anew, A and B. And then now we can say, oh, after step 7, A and B and C. Okay, we could do this. And just to make sure I've got all my ducks in a row, here's what that would be for all of these. And a couple of and-ins here, 2 and 4. And here's the last one, 6 and 5. All right, so in order to, and what we're in effect just doing was just picking up the parentheses and moving them. Well, that's precisely what associativity allows us to do. So what that means is, if I want to move these parentheses, you know, as long as it's dyadic, if I've got all ands, I can just pick up the parentheses and move them. Okay, so this is a shortcut there. Remember that took, we were done by step 7. Well, now you can just say this, law of association on line 1. Okay, and it works in either direction. You could start with this. Okay, so you could have, it could be a heavy left or heavy right. You can basically just switch it from being a heavy left to a heavy right. Okay, now that works with ands. It also works with inclusive disjunctions. Let's say we had A wedge, B wedge, C. Now they all have to match. You can't start mix and matching ands and wedges. Literally, that's what distribution just was, where there was a mix and matching of dots and wedges, of conjunctions and disjunctions. So they have to all match. So I've got all dots here. I can move the parentheses around. Let's say I was given this. Yep, I can just pick up the parentheses and move them. Now, whereas in the last problem, or the last one I did, the one that I did here a moment ago with the dots, that one's pretty easy to move the parentheses using nothing but the basic rules. Okay, we basically do a couple of and outs and start doing some and ins. This is much harder to move because remember, wedges don't just break apart. So you have to, this is actually a pretty complicated proof to do relative to this one in order to make this work. Like it takes a while. It takes some doing. So this ends up being much helpful, a very helpful shortcut here. Also, this works with all XORs. It actually ends up being an even more helpful proof. So if I've got all XORs, I can just pick up those parentheses and move them. That's fine. All of these. Association on line 1. So associativity is just moving the parentheses around. Now, and remember, it works for you got all ands, you got all inclusive ORs, or you've got all XORs. You can't mix and match between them. And then, oh, what about things like arrows? No. What about double arrows? No. So only conjunctions, disjunctions, whether they be inclusive or exclusive, are associative, or can be represented, are instances of connections that bear the associative relation. So basically, the short version of this is you need to pick up some parentheses and move around. Now you can do that really easily. Okay, and the next rule is kind of like this too. Something that would have been nice to have back on quiz 2. Let's take a look. All right, the last member of our law trilogy here is the law of commutativity, or we can call it commutation, we can call it the commutative property. Any of those are fine. Okay, and we'll be abbreviating it here as LC. Okay, so commutative is like an even simpler, it's kind of like association except even simpler. Here's what we can do in terms of commutativity, and let me do this the route kind of similar to how I showed association. Let's say I had this, A and B, okay, and I said get B and A. Flip it around. What would you do? Well, you break it apart. Okay, A and B, that's and out on line 1, and out on line 1. And then we could put it together the other way, B and A, and in 3 and 2. Yay, we did it. And then we could do it in the other direction as well. And so commutation here is a shortcut that just says, hey, if you've got an and, you can flip the constituent components around. You got A and B, you can totally just say B and A. Okay? But that's not all. So this is the one where it's this saves us a couple of steps here. It shaves off a few. For ands, it's a little bit helpful, but again, just like association, for inclusive and exclusive disjunctions, it's really, really helpful. So what the law of commutativity allows you to do here is go, hey, you got A wedge B. Well, then you can also say, let's B wedge A. Assumption, commutation, line 1. It also works with XORs. Okay, so if you had A XOR B, you can flip that one around. This also ends up saving you a lot of time, because this proof otherwise is much more difficult to do than you might think. Law of commutation, line 1. So these are all commutative. What's not commutative? Arrows are not commutative. If you have A arrow B, you cannot just switch it to B arrow A. Not the same thing. Okay, so if I said something like, if today's Monday, then we have a test. Oh, we have a test, and today's Monday. No, it doesn't mean like every time you've ever had a test throughout your entire life that all of a sudden that makes it Monday. All right, so you don't want to invert those. So they're not commutative. Just like in arithmetic. So this isn't algebra, this isn't calculus, nothing complicated. Addition and multiplication are always commutative. So if I say, 10 plus 5, and I say 5 plus 10, they're commutative. So what are they? They're both 15, right? So here's the commutative property in arithmetic. Okay, addition and multiplication are always commutative. Subtraction is not commutative. So if I say 10 minus 5, that is not the same thing as 5 minus 10. Okay, because in this case we've got 5, and in this case we've got negative 5. Okay, so thinking back to math that you've been doing since you were in elementary school, all addition and multiplication is commutative, whereas division and subtraction are not commutative. You could even take that with association as well. In arithmetic, multiplication and addition are really they bear the associative, commutative, and distributive properties. Division does not in the same way. Okay, it's not commutative and it's not associative, and it also doesn't bear the distributive property. Now you might be thinking, what about double arrows? Well, isn't A arrow double arrow B the same thing as B double arrow A? It is, and I'm going to call this, it's ostensible commutativity. Okay, obviously it looks like you're flipping around, but what's going on here is mechanically a little bit different. Okay, the reason why we can flip it, so on the surface it looks commutative. There is a way to do this, but we'll get there. It's going to be material equivalence. That's how it's one of the forms of material equivalence, because the way arrows work, technically something different's happening there. So I'll just say this: for commutativity, you got dots, you got inclusive ORs, you got wedges, you got XORs. You can just flip the pieces around, and that's the law of commutativity or commutation, or the commutative property. All right, now let's look at a hypothetical syllogism. This is also called a chain argument. I like to think of it also as a train argument. So let's take a look at one of these. This is something, I think this goes back to quiz 3, a problem like this. We've got A arrow B, B arrow C, and I want you to get A arrow C. So what we'd have to do before is we'd have to do an arrow in. You know, we'd pop in an A here as a provisional assumption. We'd go after that right side, which is C. We'd get out B, arrow out 1 and 3. Then we'd be able to get out C, arrow out 2 and 4. And then we could go, yep, A arrow C, that's the thing, arrow in 3 through 5. Okay. Hypothetical syllogism allows us to do this much more quickly, immediately. Because, take a look at what's really going on here. All right, so look at my first assumption. A leads to B. And my second assumption is B leads to C. So really what I'm doing here is I'm just kind of cutting out the middleman. I'm saying, okay, if A leads to B and B leads to C, then I can just say this, and I can, so to speak, cut out the middleman. So that means this is true. That's all that's going on here, which is why I can say in line 3, I can just go A arrow C. Hypothetical syllogism 1 and 2. Okay, and so again, you can think of it as, you know, if you've got if you're consequent somewhere, you have a right side that's also a left side somewhere, you can just cut that out and make the arrow attached that way. Okay, A arrow C gets to the end. Okay, this one's pretty straightforward. So, like if I said, the example that I have, if I'm tired, then I'm cranky. If I'm cranky, I'm difficult to be around. So if I'm tired, then I'm difficult to be around. There you go. Let's take a look at the next one. All right, this one, impossible antecedent. It works this way. Let's say I had this. A arrow B, and I had A arrow squiggle B, and I said, solve for squiggle A. Well, what we'd do before is we'd say, okay, let's do an indirect proof, provisionally assume the opposite of our goal, and then we want to get any contradiction. It'll be real easy because we get a B real quick. We also get a squiggle B. That's arrow out 1 and 3, and arrow out 2 and 3, and then what we can do is we can just stick these together, B and squiggle B. Okay, and in 4 and 5, and so then we're able to say, through an indirect proof, zoom out and go, yep, squiggle A is a thing, indirectly, 3 through 6. So impossible antecedent is actually a shortcut in this case, because look what's going on here. Because of an indirect proof, we know there's a problem with what's going on here. Let's see what I mean. Because there's actually kind of an indirect proof sort of staring us in the face already without us having to draw it out in all those steps. So look at this. A leads to B. A also leads to not B. Well, how could that happen? How could something lead to something and lead to the exact opposite thing as well? That doesn't make any sense, because that would lead to a world where B is happening and not B is happening. A is leading to a contradiction. That's why we know squiggle A is true. So that's why we can say if you've got an arrow, left side of an arrow that's leading to something and the exact opposite, then that left side is not a thing. Impossible antecedent 1 and 2. Now we know this works because if we did the indirect proof, we'll get the same result. So what we can just say here, the short way of saying this is, if you got something where it's on the left side of an arrow and it leads to something and it also leads to the exact opposite thing, that left side of an arrow is not happening. Okay? Let's take a look at the next one. All right, let's take a look at biconditional transitivity, or a biconditional syllogism. So really this is a hypothetical syllogism just for double arrows. And actually, hypothetical syllogism itself, what was going on there, that chain argument, is another one of those laws. Like, remember we did association, commutation, distribution. This is the transitive property. Basically, if you got something on one end, you can get to the other end. It doesn't work with ands or ors, but it does work with arrows and double arrows, as we're going to see here. So here, like this one, if we had A double arrow B, and we had B double arrow C. Okay, and let's say I wanted to get A double arrow C. So this is, again, just like the hypothetical syllogism one that we did a little while ago, just with double arrows. Now here, we'd have to do more work to get here. So look, we'd have to do this. We'd have to go, okay, that would break down into this and this. Okay, double arrow out on line 1 for both. This one would break down into this and this, B arrow C and C arrow B. Okay, and then what we could do here is we could actually use hypothetical syllogism here to go, oh, look, A leads to B, B leads to C, so we can say A leads to C. Hypothetical syllogism. This actually saves us some space here. Hypothetical syllogism 3 and 5. And then we could also say in line 8, C arrow A. Okay, another hypothetical syllogism from 6 and 4. And we could do it without the hypothetical syllogisms too. It's just we're gonna have to make some arrow ends, and it ends up being a lot longer. So I'm allowing that here to show you, even with using that hypothetical syllogism, this takes 9 steps, even if we do these. If we don't do the hypothetical syllogisms, it takes even longer to do this. Okay, and so this would be double arrow in 7 and 8. So what's the easier way to do this? Biconditional transitivity, this. Double arrow S. Okay, so look, you got, here's what's going on here. Here's the way that you should do this. If you got this situation going on, okay, and again, it's kind of like a hypothetical syllogism, like A leads to B, and B leads to A. Like, this is an if and only if situation going on. This leads to this. So if A is equivalent to B, and B is equivalent to C, then we can just cut out the middleman and say, well, then A is also equivalent to C. We don't have to jump around. What is that? Biconditional transitivity, biconditional syllogism, lines 1 and 2, rather than doing all of this. And again, if we don't use the hypothetical syllogisms and we do arrow ins instead, you've had a problem like this before on quiz 5, I believe, and it was more steps than this. Again, now you can be done by step 3. Makes this a lot easier. All right, converse inverse transposition allows us to do this. This is problems that we've had since we've been able to do indirect proofs. So we've done one like this before, and this one saves us a little bit of time. So let's say I had this, and I said I want to get this. Okay, what we would do in the past, okay, it's an arrow, so we'd provisionally assume the left side. Provisional assumption for the left side, so we're going to go after squiggle A, and then if we immediately do a modus tollens, we get squiggle A, and we have an arrow in that's done super, super quickly. All right, modus tollens 1 and 2. Let me label these 2, 3. And so line 4, we can say squiggle B, arrow squiggle A, arrow in 2 through 3. So we've had that one for a while. In fact, you had one like that, I believe, on quiz 4. I think you had a problem that was almost exactly like this. It might have been different letters, but it was basically the same idea. Transposition just says this. You got an arrow. You can flip the sides around and just change their left and right slots. So it's kind of like those De Morgan's law and material implication and conjunctive conditionality. It's kind of like one of those, except we're going from arrow to arrow. So we're not changing the symbol at all. It just says this. If you take the parts of an arrow, if you have an arrow, what you can do is you can flip the parts around and change the left and right squiggles, slots, and you've got the same thing. So that's why I can say here, like, if I have, like in the example, if you're 21, then you can legally drink alcohol. It's the same thing as saying is you can't legally drink alcohol, then you're not yet 21 or older. Okay, so that's what's going on here. Now the next one is like this too, just with double arrows. The principle is the same with double arrows, although with double arrows it's a little bit weird because double arrows, there's really no real left or right technically. Left or right ends up being a matter of being arbitrary. Well, I'll show you what I mean here. All right, let's take a look at biconditional transposition. So just as we learned a moment ago with arrows, you can flip them around, and as long as you flip the left and right negation slots, you can totally flip arrows around. It works the same way with biconditionals, except we don't even need to flip them around because since they're double arrows, each side is the left and the right. That's kind of what a double arrow means. So what we can do here is we can just, with biconditionals, we can just flip both of them. We can just say, yeah, that. And vice versa. I mean, I could switch sides here if I wanted to. I could put the squiggle B on the left and the squiggle A on the right. Because they're double arrows, it really doesn't matter. Now, I have some that might argue, oh, isn't this really material equivalence? And you'll see that there's some weird stuff going on with double arrows when we get to material equivalence. I think what's going on here is a little bit different, so I'm calling this biconditional transposition. And so, what would something like this mean? So, say it's a square if and only if it has 4 equal sides. Okay? All right, so that means if it's a square, it's got 4 equal sides. If it's got 4 equal sides, then it's a square. Cool. Okay, but that means that's the same thing as saying if it doesn't have 4 equal sides, then it's not a square, and if it's not a square, then it doesn't have 4 equal sides. Yep, that works. So again, the more technical way to say it, reading it as it is, it's a square if and only if it has 4 equal sides. If it's not a square, it is not a square if and only if it doesn't have 4 equal sides. So yep, biconditional transposition just allows us to take the double arrow and just flip both negations on, and those meanings are equivalent. All right, we could also start with this one and work here. And it doesn't matter, we could have moved the A over to, again, instead of this is a line 2, I could have said, so an alternate line 2, I could have said squiggle B, double arrow, squiggle A. That's just as fine. Same thing. It works. Okay, if you really want to switch it around, because with double arrows it doesn't matter. Take a look at the next one. All right, let's take a look at disjunctive syllogism. Disjunctive syllogism is probably one of the most helpful of these new rules. Now, in some cases, it saves you just a little bit of time. So let's take a look at one of the versions where we have an inclusive disjunction. Let's say we had this. A or B, maybe both. Not one. Okay. Scribble A. What do we know? Well, think about it. Like if I say something like, I'm snacking or I'm studying. I'm not snacking. What do I know? Well, then I know that I'm studying. And so I can say here, that's disjunctive syllogism 1 and 2. And actually, without using disjunctive syllogism, we can see this one pretty easily by doing this. If I had it, and I had squiggle A as an assumption, I could turn this into an arrow, okay, with material implications, squiggle A, arrow B, that's material implication on line 1, and then I could do an arrow out, and I get B. Arrow out, 3 and 2. So it saves me a little bit of time there. So this is one form of disjunctive syllogism. Okay, so the way it has to work when we have disjunctive syllogism, when we have an inclusive or, if you have negation of one of the disjuncts, you can say, then we have the other one. Let's look at some other versions of disjunctive syllogism that we can do. If we have an exclusive disjunction, it means something a bit different. Take a look at a version of this where we've got an exclusive disjunction, and I'll start off by saying, I'll start off with one where it's very similar to what we just saw with the inclusive disjunction. All right, so if I say something like, I'm going to Cambridge or Oxford, but not both. I'm not going to Cambridge. What do I know? I'm going to Oxford. Okay, disjunctive syllogism, 1 and 2. But now the proof to get this otherwise is much more difficult without this rule in play. It would take much longer to figure it out. The proof would be very, very long. All right, but also, with exclusive disjunctions, we know this too. If I had A, X, or B as an assumption, and I said one of these things positively, okay? So if I said the Earth is, round or flat, but not both. The Earth is round, so what does that mean? It's not flat. Disjunctive syllogism 1 and 2. But this time, here I'm saying I have an affirmation of one of my disjuncts. If it's exclusive, this works. Here's where it doesn't work, and I want to make sure this is clear. If I have something like, with an inclusive disjunction, I say one of them positively, we cannot get the other one. So if I say, like, we've got a quiz Tuesday or Thursday, maybe both. Oh, we got a quiz on Tuesday. It does not follow that we don't have a quiz on Thursday. That does not follow. We might. So when we're dealing with exclusive disjunctions, if we have a negation of one, we can definitely have the affirmation of the other. And if we have the affirmation of one, we definitely have the denial of the other. But with inclusive disjunctions, all we can say is that if we have the denial of one, either one, we can say definitely, yep, we've got the other one. So right here, these are the three legitimate forms of disjunctive syllogism. All of them save us a little bit of time. The thing I want you to note is that if you have an exclusive disjunction, you could either say not one, you definitely got the other, or you've got one, then you don't have the other. But it doesn't work that way with inclusive disjunctions. There, with inclusive disjunctions, only in the case that we have a denial of one can we say positively, yep, that means we've got the other one. Okay, conjunctive syllogism is basically disjunctive syllogism with where we have a not both statement and we're just skipping a De Morgan's law. So, for example, if I said this, you can't have A and B, but you've got the affirmation of one of them. Okay, you can't have both, but you've got one of them. What does that mean? Well, what we could do is we could do a De Morgan's law here, and we would get, oh, that's squiggle A, a wedge, squiggle B, De Morgan's law on line 1. And now what we could do is we could say through disjunctive syllogism, oh, we've got, you can either not have A or you don't have B. We know A is true, so we know that squiggle B is the case. Okay, and that would be disjunctive syllogism 3 and 2. Okay, so like let's say you can't be both a Democrat and Republican. You're a Democrat, and we switch this to you can't be either not a Democrat or you're not a Republican. You're a Democrat. Well, then that means you're not a Republican. Okay, that works. But conjunctive syllogism just allows us to do this a little bit more quickly. So think about it. If you're saying you can't be both these things, well, you've got one of them. Well, then we know that the other one can't be. Okay, and that's conjunctive syllogism 1 and 2. The thing I want to emphasize here is it only works if you have a affirmation of one of them. So what doesn't work? Let's say you had this. You got squiggle A and B, you can't have both, and you have the denial of one of them. That doesn't mean that you have the affirmation of the other one. So in short, you got a not both statement. That does not mean that you can get, if you got a not both statement and you have a denial of one of the pieces, all right, so you got not A, you could also have a squiggle B here instead. It does not mean you cannot derive the other one. Neither can you derive the negation of the other one. It does not work. It only works in this way. You got a not both statement and you say, I do have one of them. Then you can say, then you don't have the other one. That's the only way it works. Not both. I got one. Okay, so you know, not the other one. Okay, you can't have both the soup and the salad. All right, let's say they enforce this period. You can't have both the soup and the salad. You have the soup, well then you don't have the salad. Okay. Now again, what about an upcharge? Well, just think of it. Imagine it this way: you can't have both. Period. Okay, no exceptions. Well, you got the soup, then you don't have the salad. But you can't say you can't have the soup and the salad. You don't have the soup. Oh, then you have the salad. Maybe you ordered an appetizer or something else instead. Okay, maybe you don't have the salad. Well, maybe you ordered a salad independently. It wasn't like a menu option that was derived from like a combination choice on the menu. All right, so it doesn't follow. So this doesn't work. The only way conjunctive syllogism works, you got not both statement, and you say I have one of them. Then you can say not the other one. It's the only way that it works. Sentence is a word that literally means it has the same power. So let's take a look at a couple of examples. It works with, I'm going to go ahead and say it works with dots. It works with inclusive disjunctions with wedges, and it works with arrows. And this is where simply you have tautologies, where you say something redundant and it means the same thing simplified. We've already kind of seen this. Idempotence is kind of hiding in the redundant wedge outs. So it means stuff like this. If you say, let's start with the and. If I say A and A, it's Wednesday and it's Wednesday. Well, guess what? That is the same thing as saying it's just Wednesday. Okay. Now I could start with this one. It's Wednesday and it's Wednesday. Well, that's the same thing as just saying it's Wednesday. This is I think the well-formed form here. But I could also start with it's Wednesday means the same thing as it's Wednesday and it's Wednesday. It's ridiculous to do that, but you could. It also works with inclusive disjunctions. So it's Wednesday or it's Wednesday, maybe both, means the same thing as just it's Wednesday. But I could also, with wedge in, I could also do it the other way. I could say it's Wednesday, so it's Wednesday or it's Wednesday. Maybe both. Why would you want to do that? I don't know. But what this does, this is what allows us. This idempotence is hiding in this rule. When you see this thing that we've been doing for a while, okay, when I said you can just say, oh, you technically get C wedge C here, but I said you can just say, it's the same thing as just saying C. That's because there's an idempotence hiding in here where it's redundant. It also works with arrows. If I say, if today is Wednesday, then it's Wednesday. So it's Wednesday. So in any case, where you have a redundancy, where you're saying the same thing twice, it's a table and it's a table. It's a table or it's a table. Maybe it's both. If it's a table, then it's a table. What do you got? It's a table. That's idempotence. All right. Basically, it's a thing that says if you have these kind of redundancies with an and, with an inclusive or with an if-then, the redundancy collapses into just itself. That's fine. So in order to prove that we could go between these two, we'd have to do two separate proofs. First of all, we'd have to provisionally assume A in order to get B arrow C. Okay, now with this A here, then we have to do another provisional assumption of B in order to get C. And then we could say, yeah, A and B is a thing. And in 2 and 3, then we could do an arrow out and get C, arrow out 1 and 4. And then we could say here, yep, if you've got B, then you can get C. And so we can zoom out and say, yep, if you got B, then you can get C. Arrow in 3 through 5. And then that allows us to also say, to zoom out here and say, yeah, if you got A, you can totally get B arrow C. But this rule also allows us to go the other way. Okay, that's arrow in 2 through 6. We can also go the other way. What's that look like? And so going the other way, it looks like this. We'd have to go, all right, provisional assumption, A and B. All right, provisional assumption of the left side of our goal. This is also an arrow in. So provisional assumption, we'd have to go after C. Break this apart. And out on line 2 for both. Do an arrow out. We'd get B arrow C. That's arrow out 1 and 3. And do another arrow out. We get C. Arrow out 5 and 4. And then we can say, yep, it's a thing. Zooming out. If you got A and B, it'll lead you to C. Arrow in 2 through 6. And so what exportation allows us to do is to go in either direction and skip both of those proofs that I just said and I just laid out. So exportation allows us simply to say, if you got this, it's the same thing as saying this. And you can just do that in one step. So if you've got A and B, arrow C, as an assumption, you can simply just say A arrow, B arrow C. Okay, what would that be? XB on line 1. And you can also do the vice versa. So if you started out with A arrow, B arrow C as an assumption, you can say, yep, that's the same thing as saying A and B, arrow C, exportation on line 1. It works in both directions, save you several steps. Let's take a look at absorption. All right, let's take a look at absorption. Absorption says this: if I'm anxious, then my heart rate will go up, as an example. It's the same thing as saying, if I'm anxious, then I'm anxious and my heart rate will go up. So what I can do here is with a couple of provisional assumptions is I can say that these two things are equivalent, and that is absorption. Alright, let's take a look at disjunctive saturation. This one's pretty straightforward. You got this, A wedge, A and B. Then you can get just plain old A. And so let's think about it here. Like if I've got it's Wednesday or it's Wednesday and I'm tired, what do I know? It's Wednesday. Regardless of all else, I can determine it's Wednesday. How so? Sat, line 1. Saturation, the disjunct here is on both sides of the disjunction, so it ends up getting saturated unto itself, and so I know this is what's ultimately the case. So consider this for resolution. I'm taking a semester off, or I'll go on vacation. I won't take a semester off, or I'm going on sabbatical. Okay? Then what that means is I'm going to go on vacation, or I'm going on sabbatical, maybe both. Resolution 1 and 2. Okay, because the kind of like the middleman here gets cut out. It's kind of like a hypothetical syllogism in that regard. Same thing works with XORs. If I say A XOR B, and also I've got squiggle A XOR B, and let's say that it would be C here. Let's say I had these as assumptions, and let's say they were I'm either in Georgia or North Carolina. I'm either not in Georgia or South Carolina. What does that mean? Well, that means I can say, certainly, I'm either in North Carolina or I'm in South Carolina, but not both. Resolution, I'm resolved at this point, 1 and 2. And let's take a look at this scenario. So let's say we have this. The streams in Aiken flow either towards Greenville or Savannah, but not both. The streams in Aiken either do not flow towards Greenville or Edisto Beach, but not both. So there I can conclude, like, all right, this one's out, and then these two are in. But when it comes to an out, I can only get an inclusive disjunction here. This resolution actually works with it. If you got all XORs going in, it works. And also, you can get an inclusive OR out here too. Okay, in fact, so an inclusive OR or an exclusive OR is a possibility as a result here with this one. So what this one is saying here in line 3 would be this. So the streams in Aiken flow towards Savannah or Edisto Beach, maybe both. In fact, they do. Okay, things on the west side of town flow towards Savannah. Things on the east side of town flow towards Edisto Beach. Okay, every drop of rain in Aiken County. All right, let's look at the next one for us, material equivalence. A lot going on here. Let's take a look. Let's talk about material equivalence. Now, material equivalence is basically a rule that is a catch-all for all the other things that we can do with double arrows. So there's a lot of things that we can do with material equivalence. There's all kinds of derivations that we can make. There's one particular element that I want to focus on, all right, that is the most important. It'll be the most useful, and then I'll talk about the other ones that we can do. So here's the main thing that I want to say. The main thing that you want to know about material equivalence is there's something here that allows us to do something kind of like De Morgan's law, kind of like double negation, kind of like material equivalence, kind of like conjunctive conditionality, that allows us to switch from something to something else. So, for example, when we're doing De Morgan's law, that allows us to switch from a wedge to an and by switching all the negation slots, outside, left, and right. There is conjunctive conditionality that allows us to switch from an and to an arrow by just switching the outside and the right. Okay? And then there was material equivalence, which allows us to switch between a wedge and an arrow by just switching the left side. So material equivalence is kind of like all of that. It does more than that too. But the main thing that I want you to know with material equivalence is it allows us to do the following. Alright, so none of this is material equivalence. These are all their own respective rules. But the main thing I want you to know with material equivalence is this. It allows us to switch from double arrow to an XOR by just switching the outside slot. So check this out. If you've got, what that means is, so this is a form of material equivalence. If you had A double arrow B, what you do is you can change that into an XOR. Watch this. You just take the letters, keep them the same, switch the symbol, change the negation slot. Which one? Outside. So if you have A if and only if B, it's the same thing as saying XNOR A XOR B. So that means if you got A is the same thing as B, B is the same thing as A, then what you're saying is you can't pick between A and B, and that makes sense because they have to be the same thing. But that also yields a couple of other combinations. If we have A XOR B, okay, you've got A or B. You got to pick one or the other. Okay, so we can say here material equivalence 1. You got to pick between them, one or the other. Then that means that's the same thing as saying take the A down, take the B down, change the symbol, negation slot. Okay, material equivalence. Line 1. If you've got A XOR B, okay, you got to pick one or the other, then obviously that means A is not if and only if B, because this would mean the same thing. So let's say like it's either a triangle or it's a square. Okay, one of these. It's a triangle or it's a square. It can't be both. Well, then it can't be the case. Then if it's a triangle, it's a square, and if it's a square, it's a triangle. Of course, that's stupid. So that's exactly what this is saying here. All right, this is material equivalence. But material equivalence also has a couple of other various combinations. This is the most important. The main thing that I want you to know is this. Right here. That material equivalence allows us to switch between double arrows and XORs by only changing the outside negation slot. That's the main. This is the way this is going to come in most handy. There are other things that we can do with material equivalence as well. So let me go over a couple of those other elements now, just in case they come into play. These are much rarer. This is the most important thing that you need to know with material equivalence. So basically, material equivalence is a catch-all for the other things that you can do with double arrows and XNORs. What are the other things? So starting with A, if and only if B, what are some of the other things we can do with material equivalence? There's a commutativity that can be done with material equivalence, or it looks like commutativity. Actually, something else is going on. So material equivalence allows us to switch double arrows around. Technically, they're ostensively commutative, like we could just switch them around just like A and B, but something else is going on here, so technically it's material equivalence. It also allows us to do, as I just mentioned a moment ago, it allows us to make XNORs. So all double arrows are XNORs. That means all not if and only if are XORs. All right, from the same principle. We'll look at that in a moment too. But it also allows us to do things like this. A, if and only if B, is the same thing as saying this one. Because of some other principles, we can say things like this. This one seems obtuse, but we can get this. That's a possibility. How? By material equivalence. Let's say I said this as an assumption. We could say that. What would this one be? Material equivalence, line 1. Here's an alternate version of line 2. We could also say something like this. Oh, this would also be material equivalence, line 1. Okay, this one's going to be much rarer, but it's a thing. Let's take a look at another alternative of what we can turn things into. This one, in case you need it. This. All right, probably not going to be needed, but if you needed to, material equivalence, line 1. And then finally another one just in case you need it. So what's going on in material equivalence here, I want to point out, that's what I'm saying, is that all of these are different ways of saying the exact same thing. And the one that I want to stress that it's the most important, the one that's going to be the most useful, is going to be this one. Okay, that's the one you most want to know here. But these are all, in case you need them. Material equivalence is a catch-all for double arrows turning into other things. So these are double arrows. Let's take a look at how material equivalence works on double narrows. So what do I mean by double narrows? Double narrows are double arrows with negations on the outside. Similar principle, but let's see the kinds of derivations that we can get there. All right, let's take a look at the material equivalence of double narrows. And so by double narrows, I just mean double arrows with squiggles on the outside. So let's say we started with this. So the first thing I want you to know, if you have a double narrow, so let's say something like, shapes a triangle if and only if it has three sides. That's the same thing as saying, the most obvious one is a double narrow is the same thing as an XOR. All right, it can't be the case. It's a triangle if and only if it has three sides. All right, so or let's say something like this. That one, God damn it. All right, let's take a look at material equivalence when it involves negations. So let's say we had squiggle A if and only if B. So what this is saying is that you don't have a double arrow. So this is something like saying, if it's got three sides, if and only if it's a circle. Well, no. Nope. So again, the example here, if you say something like it's a circle if and only if the shape has three sides. No, that's not a thing. So what material equivalence allows us to do here with this is called a double narrow. You're saying this kind of equivalence is not the case. First of all, the most obvious example is this allows us a plain old XOR. So think about this. You're saying it's not the case. It's a circle if and only if it's got three sides. No, then it's either a circle or it's got three sides, but not both. Yeah, that makes sense. That's one version. Right? And what you'd be able to do here is if you started with this or any one of these are all equally interchangeable. People say here, oh, that's material equivalence line 1. So that's one alternate version. But there's a couple of other alternates here that I want to go into. So these are all things that we could do. We could also say this. We could just flip them around. That's fine. Okay. That's material equivalence. This one seems kind of weird. We could say this. We could really negate either side. So we're saying here, if it's not a circle, alright, this one seems the most counterintuitive to me, but it works as material equivalence. Okay, squiggle A, double arrow, B. That's also material equivalence on line 1. That one works. And that one seems weird, but it works. But here's a couple other weird ones too. We're also able to get this weird alternate version as well. This. And so this is a situation where just knowing the rule is the only way I think to know that this is a thing that could happen. This, just in case you need it, material equivalence, line 1, and then I can think of one final thing that you'd need to potentially know, and that's this. Same thing turns into and A wedge B and A and B. Not squiggle A and B. That's also material equivalence on line 1. So that is how this one works with material equivalence. These are the possible options. Now, some of these are going to be rare, but in case you need them. So if you saw something, if you started, say, with this one, you're like, solve for this version right here. Material equivalence is the way to go. Material equivalence line 1, you're done. Some of these proofs are outrageously long to switch between. But having material equivalence at your disposal, especially when you're trying to switch between double narrows and XORs, and also previously between XNORs and double arrows, is very valuable. So here's the main thing that I want you to know. In spite of all this other stuff, the main thing that I want you to know is this. When it comes to material equivalence, the main thing that I want you to know is if you have an XOR, it's the same thing as saying a double narrow. Okay, through material equivalence. Further, if you have a double arrow, it's the same thing as saying an XNOR. Right? Period. They're the same thing. Now we can put negations in play here. So if I had squiggle A XOR squiggle B, that's the same thing as saying squiggle A, if and only if squiggle B. Okay, the only thing that changes when we're changing from XORs to double narrows is the outside. Okay, if you want to switch between them. Same thing here. If I had squiggle A, double arrow, squiggle B, that's the same thing as saying squiggle A, XOR, squiggle B. Same stuff. Alright? So, knowing that, we can move into our last and final rule of substitution that I want us to know, and that's dispersion. But these are all ways of saying the same thing, actually, and these are all ways of saying the same thing, actually. So now let's move into our final rule that we're going to look at, which is dispersion. Alright, let's take a look at dispersion. Dispersion allows us to do this. Alright, we got A arrow B and A arrow C. We can make that into A arrow B dot C. So it looks a lot like distribution, but it's not. This is dispersion because arrows are involved. So let's see, first of all, this root. Make sure it's a thing. Okay, what does that look like? That breaks down into this and this and out on line 1. Then we're stuck. We do a provisional assumption. Get A. We're going after B dot C. This is pretty straightforward. We get B. Arrow out. 2 and 4. We get C. Arrow out. 3 and 4. Put them together. B dot C. And in 5 and 6. And so we're able to say here with this provisional assumption that yeah, we zoom out, we can say, yeah, you got A, you can get B dot C. Arrow in 4 through 7. Alright, dispersion in the other direction looks like this. We start with A arrow, B dot C. And our goal is to get this thing, A arrow B and A arrow C. So with this assumption in place, so far we're stuck. Now we know the last move is going to be an AND in, so we would do arrow in for each of these respectively. First of all, we do this one. Go for A, provisional assumption. Get B. A arrow out. We get B dot C. And this is one of those where I'm going to do it in a reductive way. We can just say, yeah, we get B. All right, so this was arrow out 1 and 3, and then I'm able to get it and out. I'm able to get the B and out line 3. All right, so now let's get this in reverse. So let's say A arrow B dot C as our assumption, and we want to go after this. Now, it's a dot, which means last move is probably going to be an AND in. It will be. So first of all, we're going to get this, and then we want to get this. Each of these are arrows, so we're going to do arrow ins for both. So let's do this one first. Let's go provisioning assume this, and we're going to go after, in this case, B. So here immediately, arrow out, we get B dot C, arrow out 1 and 2, and then we can just do an and out. Now here I can get and out B and C. I'm just going to get what I need. I'm going after B, so I'm just going to get that. B and out line 3. Because I know I'm done now. A leads to B, for sure. Arrow in, 2 through 4. Okay, then so I got this one, check. Let's get this one now. A arrow C, line 6. Provisionally assume A, and this time I'm after C. Okay, this stuff is off limits. Only the stuff that's out of the subproof is in play. So I'm able to do an arrow out again. B dot C again. But in this case, arrow out 1 and 6. Okay, I'm able to and out this time just the C. I could get the B out again, but that's not necessary. And out on line 7. There it is. So I can say line 9, yep, A leads to C. Arrow in 6 through 8. And so then I can come over here and say, yeah, that's a thing. You can totally say A arrow B and A arrow C. And in 5 and 9. It works. And so what dispersion allows us to do is to switch between these two. Technically, I guess, if you're doing this, you're dispersing the A here amongst the B and the C, and here you're sort of agglomerating the A from the B and the C, but either way, you're fine. So if you start with this, A arrow B and A arrow C, you can just say, oh, line 2, A arrow B and C. So it looks a lot like distribution, except you have arrows involved. Okay, so that works. But then also you can say this, if you have it in reverse, if you have A arrow B and C. So this is kind of an agglomeration. You agglomerate the A out. So if you had this, you could disperse the A by saying, yep, A arrow B and A arrow C. Again, looks like distribution, but it has arrows involved. So it's not distribution, it's dispersion. So here's the example that I have. If we go to dinner, then we'll see, here we go. If we go to dinner, we'll see a movie, and if we go to dinner, we'll have ice cream. So, if we go to dinner, we'll see a movie and have ice cream. All right, that works. And in the opposite direction, if we go to dinner, we'll see a movie and have ice cream. It's the same thing as saying, if we go to dinner, we'll see a movie, and if we go to dinner, then we'll have ice cream. So it works. This is dispersion. So everything that I've set up to this point, these are all the extra rules. These are the advanced rules. Some are more important than others. Like, for example, distribution is essential. It saves so much time. Remember, the proof that we did for distribution took 39 steps. If you can see an occasion where distribution is helpful, do it. It will literally save you 39 steps of work. Then some of the rules of substitution in here, some are more helpful than others. You might see occasions where dispersion is helpful, or exportation, or absorption. But also, after distribution, I have to say material equivalence and disjunctive syllogism are the ones that are going to be the most helpful. So what I'm going to do in the next video is go over how to apply these. So I've gone over all of the extra rules that I want to go over. The next video is going to be how to apply them and how to use them in proofs. So far we've just done them kind of in isolation. Let's see how we employ them out in the wild, so to speak. So that'll be the next video. Let's get into that.